Okay, the next case we are going to look at is called the Swedish method, and it is generally applied to undrained cases where we have undrained shear strength and phi is equal to 0. So in order to get this, you have to have saturated soil and undrained conditions. It can be thought of as a special case of the log spiral. If you take our log spiral equation and set phi equal to phi mobilized to 0, then this simplifies to e to the 0, or r equals r naught. In other words, it becomes, if r is constant, we have a circular surface. And so this is what the free body diagram looks like. And basically, we have the weight of this soil mass. So this soil mass here is what's sliding. The green dot is the center of gravity, and it is a distance a away from the center of the circle. And so to calculate the moment due to the weight, we take this moment arm a and multiply it by w. And then along the failure surface, we have the mobilized cohesion, which is the undrained strength divided by the factor of safety. And that is the force resisting failure. And then the normal force, sigma, it's perpendicular to the surface, and it goes straight through the center of the circle. So there's no moment. So if we're just looking at moments, we have the moment due to the mobilized cohesion along the failure surface and the moment due to the weight of the soil mass. And so if we sum moments around the center of the circle, we get WA minus CMLR. So the C mobilized times the length gives you the force, and the moment arm for that is R, and then acting against that is W times A. So that's where this equation comes from. And remember, the mobilized cohesion is the cohesion divided by the factor of safety. If we solve this equation for the factor of safety, we get F equals CLR divided by WA, which is basically the resisting moment, the resistance along the failure surface times the radius divided by the weight times the moment arm for the weights. So the resisting moment divided by the driving moment. So it's a really simple equation. And that's why it's pretty popular. Now, we don't normally, when we apply this, we don't normally treat this block as a single unit to calculate the area. Normally what we do is we cut it up into a set of slices, and then we apply that equation on a slice-by-slice basis. And when we get to our in-class exercise, we are going to set up and solve a solution in Excel for a slope using the Swedish method, using a method of slices. Okay, if you have different materials along the length of the slope, you just divide that up. Each one has if you have material number 1 along this distance with delta L1, that gives you a resistance force here, and material 2, material 3, material 4. So you just modify this equation. Instead of using a single CL, you just add them up, and that works fine. If you have a fully submerged slope, you have to change that whole slope becomes buoyant, and the W times A, the moment due to the weight, is equal to the buoyant unit weight times the cross-sectional area. That's what the capital A represents, and then the small a is the moment arm as before. So it's the same thing you do before. You just to get the weight, you just use the buoyant weight instead of the total weight. If it's partially submerged, you would break it up into 2 parts. Above the water surface, you would use the dry unit weight, and below the water surface, you'd use the buoyant unit weight. So pretty flexible. Now, if you have the circular surface and the friction angle is not equal to 0. Then it gets more complicated. We still have the weight due to the mass. We're going to call mw. So we have the moment due to the weight, m gamma, which is the weight W times the moment arm A. The moment due to the normal stress is 0 because I mentioned before all these normal stresses go through the center of the circle. And then we have a moment due to the shear stress. Now before we just had undrained cohesion, which is constant. Now the shear strength varies along the length of the circle. It's not constant. So we have to, it varies continuously, so we have to represent that as an integral. So we have the moment arm R times the shear strength times dl to get the integral. And so if we sum the moments up, we get the moment due to the weight minus the moment due to the shear stress, WA minus the integral of R tau dl. And then tau, this is the mobilized shear strength over here, so we divide by the factor of safety. And then basically we plug this term into right here in the equation, and then we pull out R because it's constant. It doesn't need to be in the integral. And then if you solve this equation for F, we get this equation here, which again is another way of interpreting this, is the numerator is the moment resisting failure, and the denominator is the moment of the weight of the slice driving failure. And so we have this equation. The problem is the normal stress, sigma, which is used right here, it varies along the length of the surface, and it's unknown, so you can't solve it directly for F. But theoretically, this is the equation we use. Now, could you come up with a way of slices to use this? You could, but we generally, there are other techniques that we use when we apply the method of slices to solve this. But, so this Swedish method is pretty much always applied for phi equals 0, but, you know, theoretically this is the equation that would apply if phi is not equal to 0.